So we've got here the Leonard-Jones potential energy graph. You got two atoms, they're being attracted or repelled from each other. And this graph compares the potential energy as compared to the distance between the atoms. And we saw last time that the lowest energy you can possibly have is negative epsilon. So that's the worst case scenario. If the particles are at rest and at equilibrium, they're just staying still forever, they have negative epsilon as their total energy. As we raise the energy, we allow them to move and oscillate. So for instance, let's say the energy was at this level. You raise the total this much, and now what are the particles doing?
Oscillating?
Yeah, we can expect them to oscillate. And under this circumstance, how do we know that at that E total, they're oscillating instead of just moving freely away from each other? How do we know they're still bonded together? What is it about this E total graph that tells you they can't just keep going out forever? Yeah, for one thing, E total is less than 0. That's not universally true, by the way. It really depends on what type of potential energy we're talking about. For the Leonard-Jones potential graph, E total being less than 0 means they're bonded. But how can you tell that visually from the graph, even if you didn't know about the less than 0 rule here? What is it about this E total graph and this potential energy graph that tells you there's only a small region of space where they can be? They can't just keep going outwards forever.
There's like a Rmin and Rmax, yeah.
We've got an Rmin and Rmax, which we can find by looking for those intersections. E total equals potential energy at these two locations. So at those two locations, kinetic energy has to be 0. Between those locations, potential energy is less than E total, which means there's some room left over for kinetic energy. Specifically at R0, potential energy is this far below E total, so there's this much kinetic energy in the system at that instant. So that the minimum potential energy corresponds to the maximum potential energy at that same location. Specifically, the difference between E total and potential energy is the kinetic energy. We can even look at that at other locations. For instance, right here, there's this much difference between E total and potential energy. So that much is the value of kinetic energy at that location. The difference between E total and potential energy is the kinetic energy at that location. And we can do that at any location. At any R value, you can take the difference between E total and potential energy. That tells you the value of kinetic energy at that location. Connect those together, we get a curve representing kinetic energy of this system at every location. Beyond that, potential energy would go above E total, so kinetic energy would drop below 0, and that can't happen. So we would just cut it off at those 2 points. That tells us that the particles can exist as far apart as this distance, or as close together as this distance, but nowhere beyond that. They're just going to oscillate in that small range of distances. Any questions on that so far? And note that in this state, as they're oscillating, they have both kinetic energy and potential energy. Their kinetic energy is oscillating between 0 and this value, 0 and this value, 0 and this value. And the average kinetic energy is going to be somewhere in between those. Same thing with potential energy. Their potential energy oscillates between negative epsilon and E total, negative epsilon and E total. The average potential energy would be somewhere between those. So if we have added energy to the system, we would say the energy we have added is both kinetic and potential energy. Even if you're not deliberately making them move faster or making them get further apart, if you add energy to the system, you're allowing them to get further apart and closer together. So that means you've increased the potential energy, and you're allowing them to move faster. So you've increased the kinetic energy. So you're really increasing both on average. Any questions on that so far? So we raise E total up to this high, they're still bonded. If we raise E total all the way up to 0, though, that should break the bond. I want to see what that would actually look like. If we raise E total all the way up to 0, we still have an R min. At the location where potential energy and E total intersect, we have a location where kinetic energy is 0. But since they never intersect again, that means we never have another R max. There's no R max here. There's no other location where kinetic energy is 0. We still get the highest kinetic energy at what location? That is, at what R value? Where should we expect the highest kinetic energy?
R naught.
Yeah, at R naught. And I would say at R naught rather than at epsilon, because epsilon isn't talking about a location. Epsilon is talking about an energy level. R naught, which is about 1.12 sigma, 1.12 times the diameter of the atom. So R naught is the location where we would expect the highest kinetic energy, because that's where we find the lowest potential energy. And the value of kinetic energy, again, is going to be the difference between E total and potential energy. In this case, that difference is just epsilon. So kinetic energy will have a value of epsilon at that location. Positive epsilon. And then between those, it's just going to look like a mirror image of the potential energy graph. So from here, potential energy goes down to the right and levels off to a minimum. So kinetic energy has to go up to the right, then level off to a maximum. Then potential energy increases slowly, then quickly, then levels off to an asymptote. So kinetic energy decreases slowly, then quickly, then levels off to an asymptote. Never quite reaching it though. Since the kinetic energy never reaches 0, that means the particles continue to be in motion as they drift further and further apart. They're going to get slower and slower and slower as kinetic energy approaches 0, but they never come completely to a stop, which means there's no point where there's no location where they stop and fall back. They just keep slowly drifting apart. So we would describe that as an unbonded situation. We've added enough energy to break the bond in the sense that the particles can keep moving apart from each other without ever falling back. Any questions on that so far? And by the way, there's a really nice bit of algebra that also explains why these graphs are exact mirror images. How exactly are kinetic energy, potential energy, and E total related to each other? Could we put those in an equation describing conservation of energy? How are we defining E total in the first place here?
E total would equal the kinetic energy plus the potential energy.
Right. Kinetic energy plus potential energy is E total. We have a graph for potential energy. We have a value for E total. So if we know both of these, we can solve for kinetic energy. So how would you isolate kinetic energy in this equation?
It would be E total minus the potential energy.
Right, just subtract potential energy from both sides. So a very convenient way to think of this is that the value of kinetic energy is just the difference between E total and potential energy. That's the difference we were looking at earlier. The difference between E total and potential energy is the value of kinetic energy at that instant. Alternatively, you can reverse the order of subtraction as long as you're careful to keep the negative sign on the same thing. So we could write kinetic energy as negative potential energy plus E total. And potential energy is a function. Potential energy is a function of R, this shape of function. So we're just taking a function and applying a negative sign to it. And if you think way back to algebra and the basics of graphing, what happens to a graph if you take a function and apply a negative multiplier to it?
It mirrors it on the x-axis.
Exactly, it mirrors it across the axis. So if you've got a potential energy graph and you apply a negative sign, that just takes that graph and flips it across the axis. Then we're also adding E total, which is a constant. And what happens to a graph if you add a constant to a function? Like if you're graphing y equals x squared, and then you instead graph y equals x squared plus 5, what does the plus 5 do to the graph?
Does it shift the,
Yeah, that's just going to shift the graph, in this case, straight up. Like if you graph y equals x squared, and then y equals x squared plus 5 is just going to be the same graph shifted 5 spaces up. This x squared basically tells you the original y value. We're taking the original y value and adding 5. We're moving 5 spaces in the y direction. Exact same graph, just 5 spaces up. Or in this case, shifted by a value of E total. If E total is negative, though, what we're going to do is we're going to take our potential energy graph, flip it exactly mirrored across the x-axis, and then shift it down because E total is negative. So our kinetic energy graph would be an exact mirror image shifted, so its asymptote is now E total instead of 0. But also, what's the restriction on values of kinetic energy? Kinetic energy can't be negative. So we'd have to cut off everything below the axis. And so this is our actual kinetic energy graph. The kinetic energy graph literally is just the potential energy graph reflected across the axis, shifted by an amount equal to E total, and then cut off below 0. So this is a very useful algebraic way of looking at the kinetic energy graph. Kinetic energy graph is the potential energy function flipped across the axis, shifted by an amount equal to E total, and then cut off at 0 because kinetic energy can't be negative. So this is mathematically why the potential energy graph and kinetic energy graph are mirror images of each other. Any questions on that? So you raise E total up to 0, you've broken the bond. You allow the particles to keep moving forever in either direction, although they get very, very slow. If you raise E total even higher, though, let's say you raise E total all the way up to, I don't know, maybe a third of epsilon or something. Now what's going to happen to the kinetic energy graph? If we've just increased E total to a positive number, the kinetic energy graph is going to be the potential energy function flipped over. And then if we're adding a positive E total, what's going to happen? What happens to a graph if you add a positive constant? Like if we take our potential energy graph, flip it over, but then add positive 1/3 epsilon, what would that do to the graph? Yeah, it's going to shift it upwards. So we take our potential energy graph, the negative sign means we flip it over the axis, and then plus positive 1/3 epsilon means we shift it up. So we're going to have the kinetic energy graph shifted upwards. And actually, it shouldn't approach 0 anymore. Since potential energy approaches 0, plug in 0 for potential energy, kinetic energy should approach E total. So as the potential energy gets closer and closer to 0, the kinetic energy gets closer and closer to E total. So if we raise the E total even higher than 0, this is our new kinetic energy graph. There is a 0 point. There is now an R min that's even further inwards, even closer inwards. The particles can get even closer to each other if you, for instance, launch them towards each other at very high speed. Then they'll bounce off. They're still unbonded. It's not like adding more energy breaks the bond again. It's just the bond is broken and it's not bonded anymore. But raising the energy even higher means not only are they unbonded, but they're still moving at a pretty fast speed. Whereas if you bring E total up to just barely 0, They're unbonded, but they're getting slower and slower and slower, approaching almost a complete stop, but never quite stopping. Raise the total even higher, they're unbonded and moving apart from each other at a fairly fast speed. So adding enough energy to bring E total up to 0 breaks the bond. Adding more energy beyond that just means they're now moving faster. And that would correspond macroscopically to turning the substance into a gas and then raising the temperature of the gas even higher, allowing the molecules to move faster. Any other questions on that so far? All right, so let's bring this all together. What does epsilon actually mean? If we just describe some tiny amount of energy as epsilon, what is the significance of that? What does it mean for an amount of energy to be epsilon?
Is it the amount of energy needed to break a bond?
Yeah, you have to add epsilon worth of energy to guarantee breaking the bond. Even if we're looking at the worst case scenario where E total is as low as it can possibly be, even if it's at very low energy, if you add epsilon worth of energy, you break the bond, guaranteed. So if you have one pair of particles, adding epsilon will break the bond. Because that's really all this graph is describing. This graph is describing one pair of particles. But realistically, we're never dealing with only one pair of particles. We're typically dealing with lots of particles. So let's see what happens if we've got multiple particles in the system. For instance, let's say we have 3 particles instead of just 2. Let's say we've got this particle, and this particle. And let me label those A, B, and C for convenience of reference. And let's say these particles are at equilibrium distance from each other and at rest. They're at the lowest energy they can possibly be. How many bonds are we looking at here? How many pairings are possible here?
3.
Yeah, we've got a bond between A and B. We've got an AB bond, we've got an AC bond, and we've got a BC bond. If you want to shatter this cluster of atoms, if you want to turn the whole thing into a vapor, you'd have to break all 3 of those bonds. And how much energy does it cost to break one bond? Yeah, 1 epsilon. If you put 1 epsilon worth of energy into this, that's enough to break one bond. But it's not really going to break one bond because the energy you add gets evenly distributed to all the bonds. So to break all the bonds, how much energy would you have to add? If you want to break all 3 of these bonds, how much energy would that cost?
3 epsilon.
If we add 3 epsilon worth of energy, add energy, specifically delta E equals plus 3 epsilon. And you can think of this as heat. I mean, you can sort of think of this as work. If you imagine grabbing these atoms with tiny tweezers and pulling them apart, that would be doing work. But realistically, what you're doing is you're adding heat. You're exposing this to some higher temperature region, and heat flows into this and breaks the bonds. 3 epsilon should be exactly enough energy to separate these particles, to move them far apart from each other so they're no longer interacting, or at least no longer interacting enough to notice. No matter how far apart they are still interacting a little tiny bit. But we're assuming we're moving them far apart enough for the interaction to round off to 0. We've broken 3 bonds. We're going from 3 bonds to no bonds. So that means we had to add 3 energy to make that happen. And this is essentially how we define the idea of bond energy. We would say delta E bond is plus 3 epsilon. But we want to be able to describe not only the delta energy, we want to be able to describe how much energy the system has. And the way we do that in this unbonded system, what do you think we would want to call the value of bond energy if there are no bonds at all? If you had to assign a value to the bond energy of a gas, what would you call that bond energy as a number? Think back to the graph itself. What did we have to raise the energy to in order to break the bond? Yeah, 0. So we want to call this 0 joules of bond energy. In part intuitively because there's no bond, so we want to call it 0 bond energy. But also just to be consistent with the Lennard-Jones potential energy graph, we had to raise the energy up to 0 to break the bonds. So we want to say that a bond that has been broken has a value of 0. If we backtrack though, if we backtrack to when it was bonded, what did the bond energy have to start as so we could add 3 epsilon and get up to 0? What was the energy have been before we added 3 epsilon?
Negative 3 epsilon.
Yeah. We would have to start at negative 3 epsilon so that we could add 3 epsilon and reach 0. So in a bonded system, if the atoms are actually bonded together, we consider the bond energy to be a negative value. And this goes back again to the idea of a negative value of energy just means less energy than what we're using as the reference. Like if we use ground level as a reference point for potential energy of gravity, if you go underground, you have a negative amount of gravitational potential energy. Very similar idea here. We're using the unbonded state, the gas, as our reference point. For a gas, bond energy is defined as 0. A solid or liquid is going to have less energy than that, so that's going to be a negative amount of energy, less than the 0 that we're using as a reference. And if this is confusing, it might help to consider the idea that each bond has a negative amount of energy. This bond is negative epsilon worth of energy. So is this one, so is this one. So negative epsilon plus negative epsilon plus negative epsilon is negative 3 epsilon. And since a bond has a negative amount of energy associated with it, to destroy that bond, you have to add energy to cancel out the negative amount of energy it already has. Any questions on that so far?
Yeah, so I have one question. So earlier in the textbook, when we learned about E bond, we used the equation of the change of mass times the enthalpy.
Mm-hmm.
And that ended up giving us units in joules.
Yeah.
So what's the difference between joules and epsilon?
Epsilon is another unit of measurement, but it's equal to some number of joules. And epsilon, the exact value of epsilon in joules varies from atom to atom. So any given type of atom, any given element or chemical is going to have a certain number of joules associated with epsilon. The reason why we're not using joules, the reason why we're using epsilon instead is so we can just set up one formula regardless of what type of atoms they are. And then if we know these are, like, let's say these are carbon atoms, we could look up the value of epsilon for carbon-carbon bonds and plug that in terms of joules, and then calculate the bond energy in joules. But ideally, we want to keep it generic. We don't want to specify what type of atoms these are yet, because we want to be able to make all the calculations we can, regardless of what type of atoms they are, and then we could plug in a number for epsilon later.
Okay, I understand.
And a useful way to compare these, epsilon is the bond energy per bond, the energy it takes to break one bond. Delta H is a similar idea, but instead of delta H being the energy it takes to break one bond, delta H is the energy it takes to break all the bonds in 1 kilogram. Or if you're talking about the molar version, delta E bond equals change in number of moles times delta H molar. The molar delta H is the energy it takes to break all the bonds in 1 mole of particles. So these delta H's are very similar to epsilon, but in terms of all the bonds in 1 cluster of particles rather than just the energy for exactly 1 bond. Same idea, just on a different scale.
Okay, so it's like kind of like a macroscopic versus microscopic kind of thing.
Exactly. The microscopic version, talking about the behavior of individual molecules and individual bonds, versus the macroscopic picture, looking at the big picture of the whole object on a per kilogram basis or a per mole basis, instead of a per bond basis.
Got it.
And this is going to be a common theme, both when we're looking at bond energy and thermal energy later on, that you can look at these concepts from the lens of looking at the big picture, the whole object and its observable behavior, versus the microscopic picture, looking at the behavior of individual molecules, individual bonds, which you can't directly observe, but you can infer what's going on at the molecular level based on what you can observe at the macroscopic level. And a big part of what we're going to be doing here is comparing the microscopic picture and the macroscopic picture so we can get a better idea of how they're linked together and how this influences the formulas we're using and the results we see in experiments. Any other questions on that so far? Will the amount of energy needed to break each bond always be epsilon? Not always. If the epsilon is specifically the amount of energy to break the bond if it's at equilibrium distance. But let's say we put in particles in a different arrangement. Let's say we have still 3 particles, A, B, and C. At this point, but let's say they're arranged in a straight line. At this point, we've got an AB bond, we've got a BC bond, but also A and C are going to be interacting with each other as well. Because any 2 particles, no matter what their distance is, any 2 particles can interact with each other. So we're going to have an AC bond. But that bond is different. The particles are further apart. So what would you expect about the AC bond compared to the AB bond or the BC bond? What's going to be different there? Yeah, it's going to be a weaker bond. If the particles are further apart, the bond is going to be weaker. Weaker in the sense that it's easier to break the bond. And we can actually see this based on the Leonard-Jones potential graph again. If we've got some equilibrium distance, R0, and that would be this distance, as well as this distance. These are what we would call nearest neighbor bonds. So the nearest neighbor bonds we would always assume are at equilibrium from each other. If they were closer, they would repel each other until they're at equilibrium again. If they're further, they would attract each other if possible until they're at equilibrium again. But AC is much further apart. In fact, how would we describe the distance from A to C? What is that distance?
It'd be like 2 times the bond length in AB and BEC.
It's exactly 2 times either one of those. So 2 times R0. You could also write that in terms of sigma. You could say R0 is 1.12 sigma. So twice as much would be 2.24 sigma. But which one of those you want to use is just a matter of, is your graph labeled in terms of R0 or is it labeled in terms of sigma? And for simplicity, let's assume that this graph is already labeled in R0. So you've got our R-axis, our energy axis, and we're going to have a point at -1 epsilon. So our graph we would expect looks something like this. If the particles are a distance of R0 apart from each other, you have to add plus epsilon to bring it up to 0. But if the particles are already this far apart from each other, already 2 R0 from each other, they're already at a higher energy value because they're at this point on the potential energy graph. They're already kind of far apart, so it's going to be easier to separate them further. In fact, in this case, to break the bond, you still only need to raise the energy up to 0. That's going to be from here up to here. So you don't need to add a full plus epsilon, you just need to add some small fraction of epsilon, whatever this much is. And of course, you want to be using a more clearly labeled and more accurate graph if you can. Just based on this quick sketch, I'm guessing that's probably something like 1/5 of epsilon. So breaking the second nearest neighbor bond, breaking this 2R0 distance bond, requires only plus 1/5 epsilon instead of plus 2 epsilon. So if we take a look at each of these bond categories, we have two nearest bonds. At a cost of, how much does it cost to break one nearest neighbor bond? If you want to break the AB bond, how much energy would you have to add?
Epsilon.
Right, you'd have to add plus epsilon. So we're going to say the bond itself has a value of negative epsilon. In the sense that when it's bonded, it's at negative epsilon. To break the bond, you add plus epsilon to bring it up to 0. We also have one second nearest neighbor bond. And the value of that, since it looks like right here the value is negative, and I'm just estimating here from this very rough freehand graph. For your own work, you want to use a more accurate graph whenever possible. But let's say this is about negative 1/5 epsilon. That is 1/5 epsilon below the axis. We say this bond has a bond energy value of negative 1/5 epsilon or negative 0.2 epsilon. And if there were more bonds like that, they would also have a bond energy of negative 1/5 epsilon. And you can get that from the potential energy graph. You can also get that from the, if you have an equation, have you seen an equation for this graph yet? Something like, I don't know, 1 over epsilon to the 12th and 1 over epsilon to the 6th or something like that. Sometimes they mention this in 7A, sometimes they don't. This graph does have a formula associated with it. So you have seen that? So you could plug in the distances into that equation. That's basically an equation for converting a distance into a potential energy value. So you can use that equation to get an exact value, or you could estimate it from a graph if you have a pretty accurate graph. Either way, you get a value of energy associated with that distance. We could then calculate the total bond energy by just adding these up. 2 copies of negative epsilon would be negative 2 epsilon. 1 copy of negative 1/5 epsilon is negative 1/5 epsilon. I'll just write that as a decimal for easier adding. Negative 0.2 epsilon. Add those up. Negative 2 epsilon plus another negative 0.2 epsilon would be negative 2.2 epsilon as the bond energy of this cluster. So this arrangement of 3 atoms has negative 2.2 epsilon as its bond energy. And note that that's not the same as the energy we got for the 3 atoms in a triangle. The same 3 atoms arranged in a triangle had negative 3 epsilon as the bond energy. So bond energy is not only about the number of atoms, it's also about how the atoms are arranged. A different structure, a different arrangement of atoms can lead to a different amount of bond energy, even if it's the same atoms in a different arrangement. So you really need to know both. You need to know how many atoms there are, how they're arranged in order to get an expression like this. And then if you also know what type of atoms they are, you can look up the value of epsilon and write this as an energy in joules. Any questions on that so far? Then let's take a look at a larger cluster of atoms and see if we can work out the same sort of idea. Let's say we have, let's say 4 atoms for now. And let's say they're arranged in a square shape. And that's not really all that realistic. Realistically, if you have 4 atoms, we don't live in a 2-dimensional universe. We live in a 3-dimensional universe. So realistically, you'd expect 3 of the atoms to be in a triangle. That's as close as they can be. And where could you put one other atom? Where could you put a 4th atom where it would be as close as possible to all 3 of these? In the exact middle? If you put it in exactly in the middle, now these atoms are too close, so they're going to repel though. So we can't really put it in the middle. But think 3-dimensionally. Not just in the middle, but in the middle and out a little bit. Yeah, on top of these. So if you arrange these in sort of a pyramid shape, so if this is not in the middle exactly in between, but in the middle, and out or above, if you want to think of this as a top-down view. Then if we call these A, B, C, D, then we've got bonds AB, AC, CB that are all R naught equilibrium distance, and A to D, C to D, and B to D would also be equilibrium distance. So from the side, this would look like sort of a pyramid shape, a tetrahedron to be specific. So if you have a molecule made of 4 atoms that are all bonded to each other, it's going to be more shaped like this. However, if we restrict this to 2 dimensions, let's say we assume that we have a 2-dimensional universe and we've got 4 atoms that are arranged in a square shape. If we want to find the bond energy there, we're going to want to categorize the types of bonds. And again, for ease of reference, I'm going to label these atoms A, B, C, and D. So what atoms would we assume are equilibrium distance from each other? What would be those nearest neighbor bonds? Or how many nearest bonds would you expect if you actually draw those out? Looks like 4, right? We've got, for instance, A to B, A to C. That's basically as close as they can get. We would assume that those are equilibrium distance from each other. Also C to D and B to D. And would we count B to C and A to D? Would those count as, yeah, we wouldn't count those as nearest bonds. We still want to include those. A and D are interacting with each other, and B and C are interacting with each other, but they're going to be a weaker type of bond because they're further apart. This hypotenuse, the diagonal distance from A to D, is longer than the side of the square. So we should treat those separately. But let's start with those nearest neighbor bonds. We've got 4 copies of the nearest bond, nearest neighbor bonds, at a value of, and these are all still going to be negative epsilon each. 4 copies of a bond worth negative epsilon would be negative 4 epsilon. What is considered a next nearest neighbor? That would be just whatever pairs are a little bit further out. For instance, these 4 bonds we have so far, AB, AC, BD, and CD, those distances are all exactly R naught. But anything that's further apart from that would be a second nearest neighbor, or a third nearest neighbor, or a fourth nearest neighbor, and so on. So are there any pairs here that are further apart than that? Any pairs we haven't counted yet that are a longer distance? Yeah, AD is a longer distance. Note that that distance is significantly longer than the side of the square. And also BC would be a longer distance as well. So we've got 2 copies of a second nearest bond. And these are often described as next nearest neighbor bonds. And then you would have next nearest neighbors and next nearest neighbors. I usually find it easier to refer to them as the second nearest bonds and the third nearest bonds and the fourth nearest bonds instead. In this case, though, it looks like the nearest bonds and the second nearest neighbor bonds are all the possibilities. You can't get from A to something even further away from D because there is nothing further away than D in this case. So in this case, we count those 6 bonds and that's everything. We just need to be careful to categorize it into the 2 different types of bonds here, the 2 different distances. If there are more particles over here, like let's say there was also particles E and F, we could also count a bond from A to E, which would be longer. And from A to F, that diagonal would be even longer still. But with just these 4, we've got the 4 nearest neighbor bonds worth negative epsilon each, the 2 second nearest neighbor bonds, And we'll need a value for that. How do you suppose we could get a value for those second nearest neighbor bonds? Is this going to be the same? Yeah, we want to find this diagonal. We want to know the distance of that diagonal. We can't just assume it's the same -1/5 epsilon as we had before, because this diagonal is a different distance. It's not going to be 2 times the radius, 2 times r naught. So to do that, let's bring in some geometry. If we want to find, let's say we specifically look for the distance from A to D. So we want to know this distance. And we want to be able to compare that to distances we already know. For instance, we know the distance from A to B, and we know the distance from B to D. So I'm going to put point B here as well. We know that this distance is r naught, and this distance is the same r naught. I haven't really drawn this to scale, but the important thing is the labeling. And because this is a square, we can assume that angle B is a right angle as well. So what important fact from geometry can we use to find this missing diagonal side? What do we know about the 3 sides of any right triangle?
A squared plus B squared equals C squared.
Yeah, we're going back to the Pythagorean theorem. So let's say we call this side, let's say H for hypotenuse. If we write out the Pythagorean theorem for this, we'd have r naught squared plus r naught squared. That is, this leg squared plus this leg squared equals the hypotenuse squared. So there's our specific version of the Pythagorean theorem for this triangle. And we want to know this distance h. So how would we solve for h here? How could we isolate that h in the equation?
I square root both sides.
Yeah. If we just take the square root of both sides, that should do it. Square root of the left side, square root of the right side. So on the right side, we just get equals h, because square root and square root cancel out. On the left side, though, we can't just split this up into square root of the first thing plus square root of the second thing. Square root does not distribute across addition. But what we can do is we can combine like terms. R naught squared plus R naught squared would just be 2 times R naught squared. And that's inside a square root. And even though square roots do not distribute across addition, square roots can distribute across multiplication. So we've got a 2, we've got an R naught squared. The square root of the whole thing could be considered the square root of each multiplier individually. Square root of 2 times square root of R naught squared. Square root of 2, we would just leave as square root of 2, or about 1.414. And then square root of R naught squared becomes just R naught. So that's our distance. The distance between particles A and D, and likewise the distance between B and C, is square root of 2 times R naught, or about 1.4 times R naught. Alternatively, if you had this label, if you had the graph labeled in sigma, we could replace R naught with about 1.12 sigma. So multiply 1.4 times 1.12, and that'll get you a measurement in sigma to look for on the graph. But let's say we had that same graph labeled in R naught again. R naught, 2 R naught, 1.4 R naught is going to be somewhere in between those, a little less than half. If we once again look at the Lennard-Jones potential energy graph, look for 1.4 R naught, that looks like, and again, you'll want to use a more accurate graph if you can, but I'm thinking that looks like a little less than halfway down, so maybe negative 0.4 epsilon. Again, just a rough estimate, you want to use a more accurate graph when possible. But I'm thinking that it seems reasonable to say this diagonal bond, since it's at a distance of 1.4 R naught, square root of 2 R naught, its energy looks like about negative 0.4 epsilon. So I would say that's the energy associated with each one of those diagonal bonds in this case. Any questions on that bond energy of that one bond so far? So two bonds of this type, negative 0.4 epsilon is the energy for each one. 2 times that would be negative 0.8 epsilon. So that's the energy of both of those diagonal bonds together, both of those second nearest neighbor bonds together. That accounts for all the bonds. So if we add those up, negative 4 epsilon plus negative 0.8 epsilon would be a total bond energy of negative 4.8 epsilon. So that would be the bond energy of this entire arrangement of atoms. Meaning if you add plus 4.8 epsilon, you bring it up to 0 and break the whole cluster apart into a vapor, splitting all the bonds apart. Any questions on that? All right, that's the basic idea. Make sure you're accounting for all the bonds, categorize them by type in terms of length, and figure out the energy associated with each one of those categories. Then account for all of them, make sure you add all of them up. If you want to get some more practice on this, try the same idea with a rectangle of 6 atoms. With 6 atoms, all these distances being R naught, see if you can use the same approach to figure out the bond energy of this cluster of 6 atoms and make sure you account for every possible pair of atoms. So you're kind of including all the bonds. So give that a try to get some practice. Have a good weekend, and I will see you next week.
Thank you.
You're welcome.